Okay, welcome back to another riveting edition of Physics 150 discussion. We are going to do problem 4 in the chapter 11 problem set. So let's read that out. We have an alpha particle with a given mass and charge, moving with a velocity that's given in component form. And it enters a region where there's an electric field and there's a magnetic field, and both of those are given in component form. The question is, what is the initial force on it? So here we have a diagram, rough diagram of what the picture is that we're looking at. It's not perfect, but it's sort of just an idea to let you know that some of these calculations are not going to be as simple as perhaps problem 2, where many of the cross products were very simple. So getting to the main issue, we want to find the total electromagnetic force on this particle. Now, the total electromagnetic force on the particle is composed of two pieces. There's the electric field component, and there's the magnetic field component that we are learning about right now. Now, when you write those out for their explicit expressions, you've got Q times E is the electric field component plus the charge times V cross B. This is the magnetic field piece, which can be written as, factor out the Q. This is E plus V cross B. So the Q is given, E is given. Basically what we want to do is find what V cross B is and then add that to E and multiply by Q, and we'll have figured out what is going on there. With this problem, like I said before, there's just going to be some hairiness involved in calculating V cross B. It's not the most simple cross product that you might be able to get from just straight doing the right hand rule. So let's actually get into the nitty gritty of doing that computation. So V is going to be given to us, and V is going to be given as, I just want to make sure that I have the right numbers here. This is 2I minus 4K times 10 to the 6th times 10 to the 6th meters per second. The B field, also given, is going to have the value of 1I and plus 4K times 10 to the minus 2 Tesla. Okay, very good. So we want to take the cross product and see what happens with these. So just naively writing down the cross product, we are going to have, let's write down the first piece, 2I minus 4K hat up here, times 10 to the 6th meters per second, crossed with I, 1I is just I, plus 4K hat times 10 to the minus 2 Tesla. One thing to note is that both of these vectors are in the xz plane. So what you might expect, you might not know exactly what the numerical value will be or the exact direction, but you know it's going to be in the y direction, because the cross product of two vectors in the xz plane should produce something in the y direction. Now, positive y or negative y, we don't necessarily know just by a quick observation. That's what we're going to figure out. But I think it's good to at least look at the problem and see if you can figure out what direction it should be going in, so that you can compare at the end of the calculation to see if it makes sense. And so my guess is that this should be in the y direction in some way or form. So let's see if we can check that. Okay, so one thing that I want to do is times 10 to the 6th that you see from the velocity times 10 to the minus 2 from the B field. Those are going to combine to give a times 10 to the 4th power. So I just want to prepare you for that. So what we have is 2I minus 4K hat crossed with I plus 4K. And this is times 10 to the 4th Tesla meters per second. Now, the thing to do with this cross product is to actually FOIL it out. But remember, this is just like a multiplicative product, like a regular product, and you want to treat it as if you're FOILing, but you don't want to flip the order with which you're multiplying. So if you could indulge me for a moment, I just want to make this clear. So this is some side work. When you are doing A plus B times C plus D, this is equal to A times C, that's the first piece, plus you do the outside pieces, which is A times D. Now you do the inside pieces, B times C, plus the last pieces, which are B times D. Now, this is how you do your normal multiplicative product, but obviously, in that case, switching A and C is not a big deal because 2 times 4 is 4 times 2. But you just have to remember that when you're doing a cross product, A cross B is equal to minus B cross A. And this is something that we just have to keep in mind when we are manipulating things like this. So going back, we know that we can just do a cross product like we did before. So when you go back to the original piece, let's scroll down a little, you're going to have that V cross B is going to be equal to, well, when you do the first piece, you get, and let's go down here just to give ourselves more room. The first factor gives you a factor of 2. And then you do the cross product of those vectors. So this is I cross I. And then when you do the outside pieces, the 2 times the 4 gives you an 8. But this time you're getting a I cross K. Next, you're doing the inside pieces, so this is going to be minus 4K cross I, and then finally minus 16K cross K. And this is all times 10 to the minus 2 Tesla meters per second. So now let's sort of simplify this a little bit. Going to our original calculation, I cross I, this is equal to 0. Because a vector crossed with a vector in the same direction gives 0. So the same goes for this last term. This is also equal to 0. In the problem 2 video, I gave the full table of cross products that you need to know, the relationships of the unit vectors via cross product. And so I cross I, K cross K, those are both 0. The other pieces, we can use the fact that I cross K, so we want to use this fact. I cross K is equal to, if you do the right-hand rule, you find that this is minus J hat. But using the fact that when you flip the direction of, or flip the ordering of the cross product, you also have that K cross I hat is opposite that. So this is positive J. So what we have is the remaining terms. V cross B is going to be equal to 8I cross K minus 4K cross I, and this is times 10 to the, I guess, not to the minus 2, which is what I wrote before. It's not to the minus anything, it's actually to the 4th power. So let's correct that up here, and also you get that this is to the 4th power, Tesla meters per second. Okay, so let's scroll down a bit. And so using the fact that I cross j is minus j hat and k cross I is positive j hat, you can rewrite this as being, and we don't necessarily need to, we can write this as an equal sign. So this is equal to minus 8j hat minus 4j hat. So that's just me putting in those values. And this is times 10 to the 4th Tesla meters per second. So we can finally write this, combining all the terms, V cross B is equal to minus 12 times 10 to the 4th Tesla meter per second in the j hat direction. Now, recall that what we wanted was the force, which could be written as Q times E plus V cross B. And so in this situation, what we can then do is, now let's write down what E is. E is going to be equal to I minus 2j hat times 10 to the 4th newtons per coulomb. Now, if you actually do out the units of Tesla times meters per second, you will also find that if you do out the units Tesla times meters per second, you look up what all those are in terms of their SI units, what you do find is that that is also equivalent to newtons per coulomb. So we're just going to go with newtons per coulomb because that's a more compact notation for the expressions we're going to have here. So now our goal is to add these two things together. We have E plus V cross B is equal to, now all of these things are going to be times 10 to the 4th newtons per coulomb, so I'm going to drop that to the end of our expression. So we have 5I minus 2J, that's from the E field piece. And then from our V cross B, we have minus 12J, that's the B field piece. And these are all going to be times 10 to the 4th newtons per coulomb. So the way that you add these vectors is just whatever is next to the I, you add those together, and whatever is next to the J, you add those together. And so this ends up being, there's nothing else in the I direction except 5. And then minus 2 plus negative 12, this is minus 14J times 10 to the 4th newtons per coulomb. Now we're almost there. This is the E plus V cross B piece. What's remaining is that the force is equal to Q times E plus V cross B, and Q is going to be given to us by 3.2 times 10 to the minus 19 coulombs. So what remains is to multiply what we just got by that. So we've got that force is equal to 3.2 times 10 to the minus 19 coulombs multiplied with, want to make sure that I don't mistake the multiplication with a cross product, 5I minus 14J times 10 to the fourth newtons per coulomb. You see that those coulombs are going to be canceling out, and you're going to be left over with nothing but newtons. And the times 10 to the minus 19th is going to partially cancel with the times 10 to the fourth. And what you get is that the force is going to be, and then multiplying the 3.2 through, you get 16I minus 45J. I rounded up to 45 there. This is times 10 to the minus 15 newtons. Okay, so this was mostly just a plug and play. We recognized that the Lorentz force law, which is the sum of the electric and magnetic components, that was the formula that we wanted to solve for. And pretty much most of the things that we wanted were given to us. It was just a matter of computing the cross product in this case and adding a couple of vectors. These are manipulations we've done in previous classes, but this is just a new context in which we've added the B field. Okay, so if you guys have any questions, feel free to email me or leave a comment in the comment section. Okay, see you guys later.